Okay, we've made it to our last group of slides, and we're going to talk here about making sure you can recognize and evaluate a nonlinear pharmacokinetic situation. Okay, so what you want to do is compare what is observed to what is expected for a linear relationship. So as we did in if you want to go back and review that first group of slides where we look at as a dose or dose rate increases, if things are linear, the area under the curve or the CSS average should increase proportionally as you increase or decrease the dose rate or dose. If they're not proportional, then you have a nonlinearity, and because of the way that nonlinearity is, you should be able to tell what may be causing it. So you should then be able to determine which kinetic parameter may explain the alteration. Change in bioavailability, volume clearance, or your effect. And then be able to think, okay, could it be a change in plasma protein binding? Could it be a change in hepatic intrinsic clearance? Could it be a change in renal secretion? Those are all things that you should be able to figure out from there by investigating and knowing your pharmacokinetic relationships very well. If you need to, I did post a kind of a putting it all together slideshow that reviews all this stuff for you that you learned in 362. It's a good idea to go back and review that if you can. So what do you do about this, though? Be sure not to use an equation to make a dosing adjustment dependent upon a linear model. So remember what we've decided to do when we can assume that bioavailability and clearance remain constant, we can say then that CSS average and dose rate are proportional. Then we can set this equation equal to each other. So our dose rate is to our CSS average for our first dose rate as our second dose rate is to our second average. This assumes linearity, doesn't it? Why? I guess I don't have to spell this. This assumes linearity. Why? Because it's dependent upon the fact that these stay constant. And if you have a nonlinearity, these could be changing, either clearance or bioavailability are changing, one or the other, or both are changing so that it's no longer linear. So we can't use this approach anymore. We can't just use a proportion. That's very important to determine dosing adjustments. Same thing with area under the curve. We assume that dose and area under the curve will remain, that are proportional as long as bioavailability and clearance remain constant. And obviously, if you have a linear situation, bioavailability and clearance are not dependent upon concentration. So as your concentrations change, these should remain constant. So we can again make changes in our dose if we want to get different area under the curves. But we can't do that. This again assumes linearity, doesn't it? And if you don't have linearity, you cannot use that equation. That's where you're going to get really messed up. That's what happened in that first case when we saw that the phenytoin went up 9-fold when we thought it would go up 2-fold, when we thought it would go from 4 to 8 and it went from 4 to 36, right? That was because of a nonlinearity. We tried to use this proportional, we tried to use this equation to make our adjustment, and you can't if you have a nonlinearity, right? That's what you really have to know. So in linearity, as your dose or dose rate increases, as this increases, you're going to get a proportional increase in your CSS average or your area under the curve. This is linear, right? Nonlinear could mean that as you increase the CSS average or area under the curve, it doesn't increase as much as you thought, or it could increase more than you thought, right? This is what's happening with phenytoin. And that's why this is dangerous, because small changes in the dose or the dose rate can make large changes in the CSS average that we don't expect. So again, normally your bioavailability, volume, clearance, fraction unbound in plasma, fraction unbound in tissue, intrinsic clearance for your tubular secretion, half-life, and K will all be concentration independent. So as the concentration changes, there's no change in any of these. But if you have nonlinearities, you can see that as the concentration increases, these could go up more than expected or go down more than expected and change all of this. So you have to be on your toes, don't you? So we're gonna try to figure out what to do in this case. So I've told you how to recognize it and what not to do, but you need to learn what to do, and we're gonna do that in lab in a couple of weeks. So stay tuned. That's all, folks. Thanks for your patience, and I've got some workshop problems for you there, and some review slides for you to work on to maybe dust off some dusty kinetics that you haven't used in a while. All right. Thanks so much. Bye-bye.